student moderator for today. Our speaker is Hoyi, and he's from the Kansas State University. And the topic would be coupled pendulums, a hands-on introduction to physics-informed machine learning. And just a reminder that this session is going to last for 20 minutes, and we'll have a 5-minute Q&A session after. And if you can keep your cameras on, you should, and keep your audios muted,
That's good.
just to prevent any distraction.
Yeah. All right. Thank you for the introduction. My name is Truong. I'm a graduate student from Kansas State University. I worked with Professor Andy Bennett in this project. So today I want to share with you a hands-on assignment for an undergraduate differential equation classes. And the goal is to bring machine learning into classroom in a simple way. So let me start with the motivation. So our students, they keep hearing about that AI will transform every field, including physics, engineering, and math. And that is an interesting claim because like our students are sitting in our differential equation classes and learning about equation, all the technical, all the classical techniques, and they might wonder that is it still relevant or how does machine learning fit into all of this? On one side, we have machine learning and AI, where they are powerful tools that can model and predict based on data. And on the other side, you have undergraduate ODEs, where you have physical laws, formulas that we have been teaching for decades. So the real question isn't just which is better. So the good question is that when to use the data-driven approach, when to use the physical laws, or when to combine them. So this assignment, we give them a hands-on example to explore these questions themselves. Okay, a little bit of the course context. So this is for the elementary differential equation course at K-State. Over 90% of our students are engineering majors. That is a required course. So the students come in have been completed calculus 2, most have completed calculus 3, and this is an extracurricular activity. So that makes the student feel more comfortable trying and experimenting. So what is our physical system? So we look at the couple pendulums. So imagine you have two pendulums hanging side by side, form a shared bar, connected by a spring, as you see in the figure right here. We track the angle from vertical, theta 1, theta 2. The lengths of two pendulum are slightly different, 105, 1.05, and 1. We have equal mass, and we connect two pendulum by a spring with stiffness K. So that is our setup. And this system produces a nice, beautiful behavior where they oscillating back and forth nicely. So using our physical laws, Newton's second law and Hooke's law here, we arrive at this equation. This is a system of second order ODEs here. And this is the stage for everything that follow. So what exactly do we do in this assignment? So we ask students, we provide a user notebook for them to work with. So you can see a screenshot for the user notebook. This is from Google Colab. So we design a notebook in Google Colab where you have all the code, you have all the library, and you have all the text. Students just to look at them and answer question, or they can also try a little bit of coding, not too much. And they can see the result. They can do experiment if they want more. So that is the platform. In this assignment, you have two main approaches. And the first one is ODE model. So from the equation we just derived, uh, it produces a solution with two frequency solution with four amplitude parameter. So you have total six parameter here. And on the other side, we have neural network. So the neural network model, it learns directly from data with hundreds of parameters, and it's basically a black box. I will talk about that later. So you have two approaches. And again, the key question throughout the entire assignment is that when do we use data-driven method? When do we use equation? And when do we use both? All right. I mean, to model anything, we need data, right? So we ran a real experiment from the physics department. So this is a picture of our setup, and actually students can see it like in the hallway of the physics department, and they can try it themselves. So we set it up, we record a video, and we use the tracker app to convert video to numerical values. And then we extract the information to data. So you can see here, this is the data. It contains the right mask and the left mask here. So this is our data, real data, not simulation. And I think that's good, right? Because it makes students more engaged in the assignment. Approach one. So first, we asked students to, actually we provide a neural network. But the first challenge is that neural networks struggle to learn the oscillatory pattern from just the t input, the time input. So the solution here is that instead of just one input, the time, we make it into a vector. So we add sine and cosine to make a vector so that you form a block of inputs with more oscillation pattern here. In here, we use 11 features, three layers, the tangent activation, and the output is 31 theta 2. And again, neural network knows nothing about the system, the setup, equation. All we give them is the data, and we ask it to model it. And here is the answer, the result. As you can see in the picture here, the neural network fit perfectly for the training data, so this part, and it's behaved not very good in the test data. I mean, this is normal, right? Because the neural network doesn't know anything about any knowledge, any physical knowledge, or any parameter. And that brings us to the following observation. So we want students to see the strengths and the limitation of this approach. So the strength is the setup, no need for physical knowledge, and it can fit any training data. So that is the strength, but it comes with a huge limitation. It's really bad at predict the future, so poor extrapolation. And the parameter are hundreds, right? And that gives it nothing. Needs a lot of data. It's basically a black box. But the most important thing we want students to know is that the model, the neural network with a bunch of parameter, we cannot extract any physical meaning like the spin constant or frequency. And that is just a complicated function happens to fit the training data. So that is the point, the insight of the first approach here. So we go to the second approach. And for the second approach, we just follow what we did in class. So we have the equation, We write the system at the matrix equation system. We solve eigenvalues, eigenvector, convert eigenvalue to frequencies, and we solve for the amplitude from initial condition. And the solution is really nice. It's behave into natural frequency. So this is our solution with 6 parameter. You can see that compared to hundreds of parameters here, right? We have only 6. And actually, it's really meaningful, right? They are frequency and amplitudes here. But how do we find all these parameters? And again, we're going to solve it by gradient descent. And that is also a machine learning method, right? That is also used in neural network. But instead of like hundreds, now we have only 6 a parameter. And hopefully it will get better. So here we go. So we set up the seed for all the running so that students get the same result for everyone. And the first one produced a terrible result. So this is the result here. You can see that this is the real data, and the model is just a straight line, basically. So it's really bad. And why is it happening? And in fact, this is a common trouble for machine learning. This is sort of called vanishing gradient. You can look at the landscape of the loss function here. So the landscape has a lot of minimal local minima here. And if you start somewhere, like as your initial value start somewhere, not close to the global minimum, then you're gonna end up in some local minima, get stuck. And you can see how this is our initial guesses, just one, and the actual value is for the 3 point something, 3.1, and optimizer got stuck. So not very good. So we want students to see that, okay, it's not that easy, right? You need to make good guesses first. So that is the first task of the student, for the student. So let's get from some physics intuition. So let's assume that you don't have the spring. Let's ignore the spring. So you have the formula for one pendulum. And for this length, you can compute the frequency. That is the root of G over L here. So this is the formula. So you get 3.05 and 3.13. And we ask students to plug it in the model and see the result. Is it better, right? Hopefully it's going to be better. And also, actually, there is a check here. We can do it by just counting the number of oscillation. So you have 5 over 10 seconds. So it showed up 3.1. So it's close, right? So hopefully this is a good guess. Um, so this is the answer here. So you can see that it's better compared to the last run, but it's not perfect. It's not like huge accuracy here. So again, the reason is that you have a lot of local minimum. And if you put some initial guesses not close to the right answer, then you're going to end up somewhere not good. And we need even more better initial guesses. And here we go. So this is the one of the key component of this approach, the Fourier transform. So the Fourier transform breaks signal into individual frequency. It's like identifying notes from a musical chord. And what is the step? We just apply Fourier transform straight to data. We have the code for that. We don't need student to know any theory behind that. So we apply Fourier transform to the data. We find two biscuit peaks of the spectrum. I mean, if you look at here, you only see one, right? Intuitively, right? If you look at the picture, you only see one. But because from our solution, we know that you need two frequencies. So we pick two biggest top picks here. And we get to 3.09 and 3.21. And this is again a data-driven approach. You don't need the equation that much. And this is a note for just a note for the faculty or anyone interested. So the Fourier analysis connects naturally to PDE, so that could be a bridge to the advanced topic in the future of your classic differential equation. All right, so we get two guesses, new guesses here. So let's plug it in. So if you plug in the Fourier frequency, run it, and to see the result. And you can see that it works now, right? So if you plug in the right number, then the gradient descent give you the right answer. And you can see that this is the optimal parameter learned by the model. So that is 3.22 and 3.07. It's kind of close, so that makes sense. So the Fourier analysis here, it gives you good guesses and goes to the global minimum nicely. And of course, we want students to answer some question. We want them to compare those choices. We want them to observe that the optimal parameter are they close to initial guesses, and sort of a reflection, right? What does it tell you about combining all of this? This can be described in this pipeline. So you have the equation that gives you the solution with two frequency. From Fourier transform, you pick the highest picks, and you use that as initial guesses. And then you plug it in, gradient descent, and it provides better results. You need all of this. This is the complete pipeline. And in the Jupyter Notebook, I also provide a table comparing all of these. So you have only neural network, neural net machine learning with equation, but bad initial values. And the last component is the complete pipeline here. So we want to make sure that students know the advantages and disadvantages of each approach. And the take-home message for them going to be combining equation, Fourier analysis, and machine learning leverages the strength of each approach. So you need a little bit of the strength of all of that. For the end of the assignment, we provide a real world scenario where imagine students are engineer and they need to design a car suspension system. The system involves spring dampers, something, and they have sensor data from the tech drive. So you have some information and you have the data, but some information, some damper property are unknown, or they changed over time, right? So you have partly information of the parameters, and you ask the student if you need to build a model that predict the future, then what would you do? Would you only use equation? Would you only use neural network, or you need to use both? And you explain why and the advantage and the disadvantage of each approach. And of course, this make them think, right? Okay, we have a different situation. What should we do? And how to justify the paragraph, the answer. All right, I have 1 minute. So um, thank you. And I have several questions for us to all discuss together. Will more data help? How much do you need? Um, how much do we want to address machine learning and AI in our differential equation classes? How much do you want students to code? Because sometimes I think not all of them good at coding, right? And should we teach them to use AI to learn, to actually use AI to answer the question, like properly, to increase their learning, not decrease their learning? And I will stop here. If you have any question, feel free to ask. Yeah, thank you.